Y'all ready for math? All right, folks, Mr. Berto back with his third instructional video for pre-calculus honors. I'm sure it's not so easy to learn by a video, so just remember that you could always pause the video at any time to write down what I've written down, listen to something that I said again. As far as questions are concerned, if these videos really aren't working out for you or anything like that, send me an email, and also make sure you get on my Remind app, okay? Because you're gonna have to submit work at some point in time. We're gonna have to talk about taking attendance and things like that. We're trying to work things like that out this week at school. I'm making this video on Monday. I have a virtual meeting planned for today, so more information will be forthcoming. But I believe on the Remind app, you could take a picture of your work and send it to me, and that might be a great way for me to actually get things graded. Anyway, let me know. So continuing with our lessons, we're talking about chapter, I think it's 3, okay, applications of the derivative. We're speaking specifically about curve sketching. What's that word? Starts with R. Recall. All right, a little recall action here. As far as what we've been talking about, we talked about the critical points of a function f. I'm not going to write that down again. Okay, that's where f prime is equal to 0 or f prime does not exist, where important things are happening. But we also talked about the first derivative test. So the first derivative test of f of x, that's going to tell you two things. That's going to tell you where a function f is either increasing or decreasing. And that is respectively where the slope of the function is either positive or negative, okay? And if you know about increasing or decreasing, then you know where a function f has maxes and mins. If you hear a screaming child upstairs, that's just my 2-year-old. Anyway, so as far as the homework is concerned, hopefully you tried it. 3 problems. You should be pretty good at the first derivative test by now. Don't worry too much about the sketching. We'll speak more about sketching today, but sketching is always the most difficult part. Make sure you take that derivative, okay? Find out if it's non-existent, which we haven't seen too many times, but we did see on the first day. So, be on the lookout for questions like that. Set it equal to 0. Make sure for your crit points, you plug back into the original. Any type of point, crit point, end point, or an inflection point that we're going to talk about today, you always plug back into the original. As far as the first derivative test, okay, make sure you draw that line. Once again, I'm here and I have sock feet on a carpet. So that really stomp doesn't really sound as large as it should be for drawing the line. But regardless, here's our line right here for G prime. Make sure you indicate where G prime is equal to 0. Plug back into G prime. I'd suggest using the simplified version myself. You just want to know if it's positive or negative. You should be able to indicate increasing or decreasing by now. Relative extrema should be pretty easy. Next year, we'll have to justify these things. That gets a little bit more wonky. We'll talk about it. And yesterday, we talked about endpoints, okay? So you have to be able to figure out using the line whether it's an endpoint max or an endpoint min. And then you have to realize to plug back into the original and then compare your maxes, okay? Compare those y values, see which is biggest. That gives you the absolute max. Compare the y value, see which is smallest to give you the absolute min, okay? So number 5 hopefully wasn't too terrible. You also had number 9 and number 10. I think in your homework solution, it says g double prime of x over here and f double prime of x over here. That's the second derivative test, okay? And the second derivative test we will speak about. Okay, so let's get rocking and rolling with today's lesson. Okay, so I think this is video 1.3, trying to organize it the best I can here. But what we're talking about is we're talking about the second derivative test. Second derivative test. If you could talk about the second derivative test, we talk about the first derivative test first. I mean, first you start with the function y equals f of x. We always know that a function represents, you better be saying y values. But now we take the derivative, okay? We know that dy over dx is going to be equal to f prime of x. And remember what a derivative represents. It represents a rate of change of a function, okay? So this right here, f prime of x, is going to represent the rate at which f of x is changing. So this right here, rate at which, not rate sandwich, anybody else hungry? Rate at which f of x is changing. I think I put on about 10 pounds in this quarantine. I'm afraid to try to fit into my clothes. Anyway, so the rate at which f of x is changing. Remember, f of x represents y values. The slope always represents y values. So it's the rate at which the y values of f are changing, okay? And remember, if something has a positive rate of change, it's getting bigger. If something has a negative rate of change, it's getting smaller. So that tells you either the y values getting bigger or smaller. All right, so y value is getting bigger / smaller. Can't read that over there. That's what I wrote. Okay, bigger slash smaller. And if y values are getting bigger, that means a function's increasing. And if y values are getting smaller, that means a function is decreasing. So this tells you where f is increasing or decreasing. And that's old news. We already knew about that. That's what the first derivative test does. But now, we're going to take the second derivative, okay? That's d squared y over dx squared. And if you take the derivative of f prime of x with respect to x, it's f double prime of x. And that's not the rate at which f of x is changing, because you just took the derivative of f prime of x. That's the rate at which f prime of x is changing. Rate at which f prime of x is changing. You know, in f prime of x, that doesn't represent the y values of f. We know the derivative represents, you know, what's that 5-letter word? Rhymes with hope? Slope. Okay, so this tells you the rate at which the slopes of f are changing. Slopes of f. Okay, and that's actually going to tell you if the slopes are getting bigger or smaller, okay? Just like the first derivative test tells you if the y values are getting bigger or smaller. Second derivative test tells you if the slopes are getting bigger slash smaller. Okay, because it represents the rate of change of the slopes of f, okay? And it's actually going to tell you the rate, you know, at which the slopes are changing, okay? So it'll tell you if slopes are getting bigger, slopes are getting smaller. Essentially, that's going to tell you about the steepness of the graph, okay? And that's the rate of change of the slopes, and that's something we call concavity. So little star, star. Okay, we call that concavity. And concavity represents the rate of change of the slopes. Rate of change of slopes. You know, and that's going to kind of tell you the steepness of the graph. It's not going to tell you whether you're increasing or decreasing. It's going to tell you how you're increasing or decreasing. So this is how you are increasing or decreasing. I guess it's not you know, you could say how a function is increasing or decreasing, but, you know, we could write it that way, not the worst thing in the world. And concavity is not the easiest thing to understand at first, but it's not really too terrible if you put some time in. If you actually think about this graph right here, it's a great way to focus on concavity. Okay, so make it look a little something like this. Or it kind of looks like an inverse sine curve, but who knows what the heck it is. I'll just say it's y equals f of x. So here's our original function being graphed. We'll say it starts at little a, ends at little b, so a little closed domain. Obviously, this is 0 right there. The origin, where it all began. And you got to think about it, you know, what's going on with the slope of the function from a to 0, okay? And remember, the slope of the function, each instantaneous value, that's the slope of the tangent line. Slope of the tangent line, that's the derivative, okay? So if I draw actually a bunch of tangent lines to the graph, little kind of snippets, pieces of tangent lines right here, you can see my tangent line starts out with a slope that's pretty dang positive. And as I move to the right, the slope gets less positive, less positive, less positive, less positive, you know, and right here, the slope is actually going to be equal to 0. And now the slope gets negative, more negative, more negative, more negative. So think about it. If I was describing a number to you, and I'm like, hey, the number starts out positive, then it gets less positive, less positive, less positive, 0, negative, more negative, more negative, more negative, more negative. That number is getting smaller right there. And that's what's happening from a to 0. The slopes are getting smaller. So down here, if I say a less than x less than 0, okay, so between a and 0, the slopes are getting smaller. Mother, the slopes are getting smaller again. And if the slopes are getting smaller, that means the rate of change of the slopes is going to be negative, okay? And f double prime represents the rate of change of the slopes. And if f double prime is negative from a to 0, we actually say the function is concave down, okay? So concave down, all right? And there's two types of concavity. There's concave down, and there's also concave, very good, up, okay? And try to think about concave down, try to think about concave down, you know, try to think about an N. That really means the function's going to look like an N. And there are two ways to be concave down. You could increase concave down, or you could decrease concave down. Some people are like, oh, the second derivative is negative, you must be decreasing. No, the first derivative tells you whether you're increasing or decreasing. The second derivative tells you how you're increasing or decreasing. See, if you actually have slopes that are positive in your concave down, the function's getting less steep. You know, here the function is increasing concave down. You can see it's getting less steep. But now if you have slopes that are negative, which means the function's decreasing, if it's concave down, it's actually getting more steep, okay? So you could actually increase concave down and you could decrease concave down, okay? We'll write that over here. We could say you could be increasing concave down. I like to write conc down. All right, and if you're increasing concave down, that just means you're increasing and you look like an n, which you've seen many times, okay? Think about a radical function, y equals radical x. That's increasing concave down. You could also decrease concave down, okay? If you're decreasing concave down, where here you can see that now you're, decreasing, looking like an n. All right, and it would be a function that looks a little something like that, which you've seen before as well, okay? So if you increase concave down, you're actually getting less steep, and if you decrease concave down, you're actually getting more steep. To bring, coronavirus into this thing, I was listening to Governor Cuomo's address the other day, and he said that the number of coronavirus cases on New York State obviously are increasing, but the rate of increase is actually slowing, okay? The rate of increase is decreasing. That means that the function that represents the amount of coronavirus cases is increasing concave down, because the amount of cases is still increasing, but the slope, the rate of those cases is actually decreasing. It's getting smaller and smaller. Not the easiest thing to understand, okay? But give it some time and eventually, hopefully, you'll be there. You'll see that between 0 and b, things are just a bit different here, kind of the complete opposite, okay? Between 0 and b, if you draw some tangent lines, you'll see you start with a negative slope, less negative, 0, positive, more positive, more positive. That's what's going on with the slope there, okay? From 0 to b, the slopes start out pretty dang negative, less negative, 0, positive, more positive, more positive, more positive. And if I'm describing a number to you, I'm like, hey, that number starts out negative, then it gets less negative, 0, positive, more positive, more positive, more positive. That means that number is getting bigger, okay? So between 0 and b, the slopes of the function f are getting bigger. Slopes getting bigger. Mother, the slopes are getting bigger again. And if the slopes are getting bigger, that means the rate of change of the slopes is going to be positive. So f double prime of x is going to be positive. And if f double prime of x is positive, you're not concave down, you're concave up. Try to think concave up, like any part of a U is concave up, okay? And that's what a graph looks like if it's concave up. And there's two different ways to be concave up. You could decrease concave up, which means you're actually getting less steep. And then you can increase concave up, which means you're actually getting more steep, okay? So over here, we can now say that you could increase honk up. So that's increasing concave up, which means you increase and you look like a U, okay? And that's an exponential growth right there, to bring the coronavirus into it again. Obviously, an exponential growth as far as the amount of people that get infected. You could also be decreasing concave up. So if you want to decrease honk up, okay, that means that you're actually going to be decreasing, but you're going to look like a U, which is actually what an exponential decrease looks like, okay? So hopefully not the worst thing in the world to understand. And this point right here, okay, is actually very important, because you could see that's where the function changes from concave down to concave up. And there's a name for that point, okay? And that's a point on the original function. So that's the point 0, f of 0 in this case, okay? And that right there is a point where the function changes concavity, and that's known as an inflection point. Inflection point, or a point of inflection, okay? And an inflection point of f of x, we'll say of f of x, okay, that's a point where the concavity of f changes. Concavity of f changes. In this case, from concave down to concave up, but in some cases from concave up to concave down, okay? And if that happens, by the way, if a function f changes from concave down to concave up or concave up to concave down, that means the sign of the second derivative is going to change, okay? The second derivative is either going to change from negative to positive, or it's going to change from positive to negative. And that's the most important thing to understand about an inflection point, is that f double prime changes sign. F double prime changes sign. That's the deal with an inflection point. We're going to draw that f double prime line today in a couple minutes, okay? And we're going to look for a little sign change on it from plus to minus or minus to plus. If that happens, that means the function has an inflection point. Remember, if you get change sign from positive to negative or from negative to positive, you must equal 0 or be non-existent first. So f double prime has to equal 0, or f double prime does not exist first. with a critical point, you just realize that the second f prime is equal to 0 or f prime did not exist. That meant that there was a critical point right there. That's not true with an inflection point. The second f double prime is equal to 0 or f double prime does not exist. That's only the first piece of the puzzle, okay? You have to check after that to see that f double prime changes sign for it to be an inflection point, okay? And look, let's do this with some problems, like the homework problems from last night. Okay, if you take a look at number 9 and number 10, okay, in your little, solution that hopefully you're able to print up. Okay, if you're not able to print, I apologize. I wish there was a better way to go about stuff like this. But regardless, here we did the first derivative test on G right here, got that information. Now, let's do the second derivative test. And the second derivative test is actually extremely similar to the first derivative test. You pretty much do the exact same thing, only you don't deal with the first derivative, you deal with the second derivative. I know when we plug into the G prime line, we'll plug back into the simplified version right here to get signs. But remember, if you want to get G double prime, you got to go back to the first time you took the derivative of G, your original G prime right here, take the derivative of that, and you can see that G double prime of X is what you guys want to all grow up to be. And that would be a success right there. And look, just like before, where you check to see where the first derivative was equal to 0 or non-existent, check to see where the second derivative is equal to 0 or non-existent. You can see it's never non-existent here. It's a linear, okay, which always exists, but set it equal to 0, and we'll actually get that X is equal to 0 here. Remember, the second we got that, X is equal to -2 and X is equal to 2 before, we knew they were critical points, okay, immediately. But here, just because X is equal to 0 does not mean that it's an inflection point. You need to see the sign change in that G double prime line. Speaking of, this is where I draw the line. The G double prime line, okay, right here. Tis it bounded? No, it is not, okay? Just like the G prime line was not bounded, the G double prime line was not bounded. Just like you put all critical X values on the G prime line, you put all possible inflection point X values on the G double prime line. You could say G double prime equals 0 here, but you don't need to. Over here, I didn't write that G prime is equal to 0. You don't need to have that written. You'll see next year in AP that the lines aren't justification for anything, but they're a great way to organize your work. The first derivative test is very busy. We get that little dummy sketch going on down here that kind of helps us out. Second derivative test, we don't have things like that. Plug into the second derivative. I'll plug in a -1. 6 times -1 is going to be negative. And now I'll plug in a positive 1. 6 times positive 1 is going to be positive. And now I know where my function G is concave up and concave down, okay? It's concave up where G double prime is positive, and it's concave down where G double prime is negative. So I know that G is honk, and we'll say up. And that's going to be when X is greater than 0. I'm using algebraic notation here. Okay, so I'll continue to do that for my, concavity intervals over here. Then we know G is honk down, and that occurs when X is less than 0. And this is such an important point right here where X is equal to 0 because you could see that G double prime changed sign. That means that the graph of G, whatever the heck it looks like, it's going to change from an N to a U, okay? And that means there's an inflection point there. Inflection point. Okay, and that means we have an inflection point or a point of inflection. And that occurs at X equals 0. What's Y? We always plug back into the original, okay? Any type of point, crit point, an end point, which we'll see in number 10, and inflection points, okay? Plug back into the original. So 0, comma G of 0, which really just ends up being the, is it the origin? Yes, pardon me, it's 0, comma 12. Okay, I was thinking of a different problem there. So 0, comma 12, we actually have our inflection point. And that's the second derivative test, okay? It's kind of like you're just doing the first derivative test on the second derivative. This is the main focus, being able to come up with these answers here. We're going to use this information to sketch right now, but sketching can always be difficult, and they really don't have you do it all that often on the advanced placement exam anymore. So just try to worry about going through these. Not every problem on tests for this is going to say, do all, these things and sketch the function. They might give you a function, just ask where it's concave down. You go right to the second derivative test, draw that G double prime line, then you can figure out where it's concave down. Maybe they want to know, if it has any relative maximums, okay? Then obviously you would just use the first derivative test, okay? So these problems aren't going to be as bad and as, drawn out as you might think. If you want to get a little sketch going on, sketch! Plotting some points here, okay? So as far as what the heck this thing is going to look like, some of these points are annoying, right? Critical points, -2, comma 28, an age I wish I still was. It was the age I was when I fell in love. So -2, comma 28, and 2, comma -4. Okay, and then also, that y-intercept, which happens to also be the inflection point. So 0, 12, I don't know, maybe like somewhere around there. Do the best you can. And we know the function, we're going to graph it using these two lines. Now we can actually graph appropriately because we know the function increases, okay, from negative infinity up to -2. So until you get to that point right there, then we know it's decreasing from -2 to 2. Then we know it's increasing from 2 to infinity. But now we know how it increases or decreases, okay? From negative infinity all the way to 0, the graph looks like an N. So it's going to increase looking like an N, which should make sense, right? Because you actually want to meet up with that local maximum right there. But until you get to the inflection point at x equals 0, it's going to decrease looking like an N as well. So you can see that my function looks like an N all the way from negative infinity up to 0. Now we hit that inflection point. Now it's going to become a U. It's going to decrease looking like a U. Okay, they've been talking about inflection points, in these government news conferences. If you've been watching that, calculus applies, folks, to the real world. And then you can see that, look, it's still going to be a U. It's a U for the rest of its life. But now we know we're increasing from 2 to infinity. So it looks a little something like that, So now you could really actually start to sketch these types of functions. Moving into number 10 right over here. Number 10 is kind of interesting because when I get my f double prime of x, you'll actually see that it becomes constant, okay? Because the original function is a quadratic. The second derivative is actually constant. Just like if the original function represented position, okay, the second derivative, would be acceleration. If you're talking about the formula for a free-falling body, throw something up and then it falls down, we know that's a quadratic. The second derivative will always be, a constant because that's acceleration, okay? They call that a scalar in physics. But regardless, over here, hey, let's set it equal to 0, okay? Well, good luck setting it equal to 0, okay? This thing right here is never going to be equal to 0, and it always exists, okay? 2 always exists. It's a constant. It's a constant. Try setting it equal to 0. There's no value of x that make this equation true, okay? So 2 is never equal to 0. Never equal to 0. Which means we're not going to be able to have an inflection point, okay? So there's no place where f double prime is non-existent or equal to 0. But you could still draw that f double prime line. That's where I draw the line. The f double prime line, 'tis bounded, in this case from 0 to 3. But there's no possible inflection point values to put on there, okay? So you could really plug any number in between 0 and 3 into f double prime. I don't care what you plug in f double prime. It's always positive 2. You always get a positive back, which means that this function f is always going to be concave up, okay? So if you want to talk about f being conc up, well, don't say all reals because it's from 0 to 3 here. We'll go interval notation. I never include, okay, the endpoints for concavity or for increasing and decreasing. If you want to say f is honk down, well, never! It's like someone's trying to storm your castle, right? And you stand outside with your sword and you go, never! Okay, this thing is never going to be concave down, which should make sense for crying out math. It's a smiley parabola, right? You know what a smiley parabola looks like? Does that look like it's concave down to you? That's concave up. Okay, so that should make sense. And obviously no inflection points here because there's no way that the second derivative could change sign from positive to negative. So no inflection points. If you want to get your sketch going on here, sketch! Okay, here we know it's going to go from 0 to 3. Okay, horrible warble right there, but whatever. 1, 2, 3. Okay, and let's plot some points. We don't have inflection points this time, but we do have critical points, okay, and we have, endpoints as well. There's an endpoint at 0, 3. How high does this thing go here as far as points? Looks like 3 is the highest y value you have to worry about, so I'll get a little something like this going on. So it's 0, 3, little point for me. We know there's an endpoint at 3, 0. And we know there's a critical point at 2, -1, or 2, negative fun, which is what you're having. And here's the thing. We know this function is going to decrease from 0 to 2. X equals 0 to x equals 2. Then it's going to increase from x equals 2 to x equals 3. And we know it looks like a U the whole time, okay? So you're going to decrease looking like a U, which should make sense because you want to meet up with that little local min right there. Local min is our little dummy sketch right here. Sometimes I call it a pushy sketch for obvious reasons. Then you can see that we're actually going to increase now, and we're going to increase still looking like a U because this thing is supposed to be concave up the entire time. Okay, so really not all that interesting of a sketch right here, but that's the deal with the second derivative test. Okay, the second derivative test is going to tell you, so we're pretty much at the end of the video right here, but the second derivative test is going to tell you not when a function is increasing or decreasing. It's going to tell you when a function is either concave down or concave up, okay? And that's going to tell you how you increase or decrease. That's the rate at which the slopes is changing. So for now, kind of focus on just being able to do, problems with the second derivative test, getting this information, which shouldn't be horrible. It's like a repeat of the first derivative test. The sketching will come in time, all right? I hope that made sense to you. Like I said, get on my Remind. I think that's the way I'm going to have you guys submit assignments. I might set up a Google Classroom eventually. Keep looking at the website. Do the best you can. If you have any questions or comments, please email me, okay? It's the best way to get in touch with me. Please watch these videos, okay? I know I don't know what's going on with testing right now. We'll figure this stuff out. But what I do know is that you need to know this material, whether it's for advanced placement calculus next year or whether it's for, college calculus, if you all are going to be in college next year, which many of you are, okay? So that's our third video right here. And this is Berto signing out. Everybody stay healthy, stay safe, stay home, and hopefully I'll see you soon. Adios.